much, everyone, for joining my talk. I'm super nervous because, I mean, you guys are probably way more experienced than I am, but I'll try my best to kind of showcase a cool project that I worked on as a Dronecode intern for the past 3 months. So the topic is make a drone follow you around. How hard can it be? And first, I want to discuss why I started this project. This project was one of the first few projects that was recommended to me by Ramon, who's the Dronecode manager, and Aterian, since I was working at Aterian as well. There was this increased demand for like a fun feature to try on PX4. Like PX4 sounds pretty dry because it's like developer's platform, and I mean, you can have a drone, but like what can you do with it that's like really fun and like really like motivating and I don't know, just something that's fun to try. And Follow Me is a perfect example because it's literally following you around, and there's nothing more intuitive than that. And so I got started in this Follow Me project. And this is what the upstream Follow Me was like. And you can probably tell that it's like, it has some interesting flight maneuvers. I'm the person riding the, the bike right there. And then the drone is kind of, kind of puzzled as to where I am, and like it's like shoving around and you don't know where it's going, and then it's like flying somewhere else, and then like, I don't know. So actually there was like a couple of issues reported in a GitHub repo as well. But apparently the original commit worked pretty well because the system was more fine-tuned, but actually it was not so replicable for other hardwares. That was the main problem. So yeah, I mean, it's scary, it's jerky, and weird, if I may say. But you may think that following something is easy, but that's not true because there are so many key challenges that you need to encounter. First, we need to understand what Follow Me is about. So this is a typical screen that you'll encounter when you enter Follow Me mode. And here you can view that person is being tracked by a drone. And it has 3 characteristics, which is height, angle, and distance. And in this mode, drone is right there where the arrow is at, and the person with the phone is where the QGC icon is at. And this is a recording from this exact same flight where I had the screen capture. And yeah, this is basically how the whole system kind of like interacts with each other. And if you think about it, which signal does the phone send to the drone in order to make it follow itself? Well, that's plain GPS signal. And that's why it's so hard to track the subject, because it's 1 hertz GPS signal and you don't have any other information. And you must do a smooth transition and control all the other variables in order to make a cinematic, smooth-looking perspective, which is pretty hard. So first challenge is, of course, GPS location filtering. Let's say you walk on a path that's smooth, like S. But reality-wise, you just get 4 different data points, and that's all you get. For a drone, this smooth trajectory just doesn't exist. And you're just a point moving through space, and the drone doesn't know what to do because you're moving like this, which is impossible. I mean, in the real world, you cannot do this unless you can teleport. So it's pretty bad. And in reality, it looks like this. The upstream's Follow Me basically was trying to follow a 1 hertz position set point. Therefore, it was jerking, and it was trying to move, and then stopping itself, and then it was trying to move again, then stopping itself. And that's why the main GPS filtering problem had to be encountered. And this shows the graph of this flight, where it actually had roll set point and position set point. You can see that it's exactly bobbing at 1 hertz, which totally makes sense because GPS signal updates at 1 hertz. And so, yeah, I mean, this is basically what it does, and then drone doesn't know what to do, and then it's just like doing this. I mean, this is really precise way to describe what was happening there. But there's another problem, the follow perspective. Well, let's say you're a stalker. You want to follow someone. I mean, you shouldn't do that, but like, if you want to follow someone through a shopping mall, you gotta be pretty like smart about following that person. Like, you cannot just go like, hey, I'm in here. I mean, that doesn't make sense. Like, you want to like make a smooth transition and like sneak up to that person, and then, I mean, don't do that. But like, you just want to do like some really smart maneuvers, and don't make it just like, oh, I'm here, so you're here, and then I just go fixed offset from you. That's boring. I'll give you an example to demonstrate how complicated it can be. You're a red dot, you're moving with your phone, and the drone is the black drone icon there. Okay, let's say we follow from behind. So you move to the right, the target is there because you want to follow from behind. Oh, I hope that makes sense. And then the drone moves there. So it arrives, and then you stop, and it's like, okay, all is good. I mean, we're tracking it. But you decide to move back, 180-degree flip. Then what does the drone do? I mean, yeah, it has to go here, right? I mean, because you're moving in this direction now. But how do you get there? Do you go just straight over the head? Or do you draw an arc? How do you do it? I mean, how are you supposed to decide exactly which trajectory to follow? And you can go like this. Okay, let's say the drone was following that trajectory, but then you just decide to go north, out of sudden. Then what do? Like, your target is now there. And then you're already moving in this direction with a certain velocity vector, which cannot be braked in a, 0.1 second and then just go straight down to the next target. So this trajectory set point problem becomes really complicated as you deal with a target that's dynamically moving around and is not just a simple linear motion, a target. And also another problem is that I mentioned that it's a GPS signal, and I mean, yeah, you hope to get a clean signal like this. If you go to the left, I mean, you want to get a signal that is going left, but in reality, you get signal something like this, like it says it's going this direction or this direction, and you don't know where it's going, and you end up having a drone like swiveling around the subject because it just doesn't know where to go. And that's those are the three main key challenges that need to be encountered. So in order to fix this, there were multiple key implementations. And first one was a second-order filter. And my work is definitely dependent on other Ethereum engineers who has already done a lot of work on this. And there's a developer named Alessandro whose GitHub name is Potato. Maybe you have seen him. He actually implemented an alpha, beta, gamma filter, which actually creates a 100 Hertz trajectory out of a 1 Hertz GPS trajectory. And this trajectory, to be fair, is pretty good enough to a level where it wouldn't do a bobbing motion, because it would be precise enough to have a smooth trajectory, but it wasn't perfect. So in reality, it would look like this. You have a GPS signal, which also has a velocity component in red, and then Alessandro's PR basically created this arbitrary 100 Hertz trajectory marked in blue. And this was pretty good. I mean, this was supposed to be merged, and this was supposed to be the improved follow me. But then there was TJ. TJ is a really smart engineer who I worked with. His nickname in GitHub is T-Stancy or something, and with the guy with the throwing the fixed wing. And then he suggested that we should implement a second-order filter. And this was the revolutionary idea of this project, because it would literally create a trajectory that's like butter smooth, no jerking motions, nothing. It's just not possible. And then it would be just what we wanted to achieve. And this was the next step that we needed to take. In case you're not familiar with the second-order filter, it's basically getting position and velocity set points, and then smoothing it out to make a kinematically feasible trajectory. And here you can see that the traditional alpha filter, for example, which is commonly used, I don't know, in like Betafly for them, like they have alpha filter for PID controller steps, it would have a lot of delay because it doesn't have the velocity feedback. But having this velocity feedback, which is already offered by the GPS signal, you can actually compensate for this delay and make a very accurate trajectory that is smooth, but also doesn't have a lot of delay. And that's why the second-order filter was such an important concept. So with this, we can create, out of this blue jerky trajectory, a pretty precise and kinematically feasible green trajectory. So it's like double the, what they call this, magician. You know, it's like a double sprinkles. So velocity feedback is super important. But, of course, as the filter gets complex, there's a problem. Remember from this diagram, there's a natural frequency constant. This constant, unfortunately, you have to set it somehow. I mean, but how do you set that? That's a big problem. So actually, I had to create a whole new script where it actually reads the U-log, the flight control log of PX4, and actually use this data and then apply second-order filter iteratively with different natural frequency constants to make sure that it makes sense. I'll just show you how it works. So the blue is the raw output, and with a 0.1 radians per second natural frequency, you would get a curve like this, and this is just unusable. You cannot use this for tracking a subject. But with 0.5, it gets pretty bad. Good. 1, I mean, it's okay. 8 starts to look a bit weird, right? Because now it's trying to track the subject target too aggressively because it can have a curve with 8 radians of seconds of frequency, which makes it so choppy and like this is bad for follow me. So we actually ended up choosing 1 radians per second, but also there's some other reasons behind it. But this is a quick overview of what the decision process was like. And the follow perspective control. So here, I'll quickly jump to a poor man's GIF viewer. So here, I will show you this. So to make sure that we will have an algorithmically feasible trajectory and to make sure that we're doing something right. I mean, we didn't implement it like straight away to the drone, but actually started with a Colab script where it actually created an artificial trajectory, velocity set point, and everything. And then we would try different algorithms. Like, oh, what if we say like we want to transition to the back, to the front, and like what if we like try different methods? Like, what if we just hard set it like the bad example that I gave in the beginning? What would happen? And we just started like trying a bunch of ideas, and you know, like this, for example, may look the same as the previous example, but it's very different because it has a subtle difference of you can see that actually the target, like the raw target position set point, which is like the ideal position where the drone needs to be, is in blue circle, but the red is actually where it's commanding. And you can see that actually it's not quite getting there. But that is intentional because in practice, we found out that if you try to make it go to the actual position set point, it would always overshoot, and it would always have a problem where it would just be too aggressive, and it doesn't work, even in algorithmic stage. And so like this sort of iterative process, in the end, like made it super simple that like, oh, we know we want to choose this algorithm because we tried it in the simulation, and it's the most feasible one. And this was a very important process of the development. And this is what I mean by the different things that we tried. So purple, red, and pink are all slightly different variations of control algorithms that we tried. And here you can see that, I mean, here it's pretty doing the same, but here you can see that like the pink is lagging so much. And why is that? It's because I discussed that it's so hard to track the target's course, where the target is headed. And if you don't have a good hysteresis on the target's course, then it can actually mess up the perspective angle calculation, and it can do really weird stuff. And you can only find this out by trying edge cases in the simulation, and that's why simulation was so powerful and useful. And in the end, we went for the purple one. And even the angle calculation itself, I said that you cannot hard set it, we tried a lot of things. In the end, we settled on a jerk limited trajectory generated angle calculation, which basically means that if we want to go to the red, but we calculate the blue. And how do we calculate the blue? It's by calculating with a bang-bang algorithm, which basically applies a maximum or minimum jerk, so like minus or plus 4 meters per second to the third derivative, and then integrating it to the velocity and position, acceleration, velocity, and position, and then you'll get a very smooth trajectory that will try to get there, but wouldn't be so aggressive. And the target course tracking I just mentioned, we tried a lot of different methods, but in the end, already the second order filter removed the problem of having all these like weird artifacts. So that was good, but in the end, the most feasible algorithm was to just freeze the target's course if its velocity is too low, and then just hard set it once it goes out of the threshold. And this may seem like why don't you have a bit of a like hysteresis where you can actually, I don't know, like smoothly track the target's course when it goes out of bounds, and you know, we tried a lot of stuff, but in the end, it just works the best in this way. And if you're up for it, please, I'll be open for contributions. And of course, there are other problems. Actually, QGC has a major bug. While testing, it was figured out that there's two different altitude reference points in GPS. There's an altitude above mean sea level, and there's an altitude above a geoid. And geoid is an artificial, you know, like a very smooth, like, I don't know, like, you know, some squishy, like, sphere-looking thing, which is not the real Earth. But QGC thinks that the Earth is like a squishy little thing, and then you end up having a wrong altitude, which is like 70 meters in, you know, 60 meters in offset. So you cannot use follow target, obviously, because the drone is going to follow you like 60 meters up in the sky, and it's not going to work. But this was a Qt bug, actually, so I couldn't, in the end, have time to solve it. But this is something that definitely needs to be solved that I discovered throughout the process. So this graph like just shows that the follow target message that you receive from the phone, which is, I think here, is actually different from the real altitude that it should be reporting, which is, you know, I got it from the PX4's GPS receiver, and that's why currently you cannot try the 3D tracking, because it might literally plunge to the ground and, I don't know, cut your lawn or something. You know, that's dangerous. But with this whole thing, now you can do this. You may be interested in this. First, you can do the RC adjustment. By having a drone, now you can adjust all the 3 components of follow me mode. You can move the throttle up to increase the altitude and down to decrease the altitude, and pitch up to make it go further, and then pitch down to make it come like closer to you, and then roll right and left to make it go to different angles. And this is super fun. I'll show you, because you can set the height to 30 meters, and then you can get shot like this. Like, this was not possible with the previous implementation because you just don't have control authority to fine-tune your follow perspectives and follow me characteristics. And you know, the yaw is very bad, I agree, but that's exactly because of the target course estimate problem that I mentioned. And still, it's not 100% solved, but I'm certain that over time, I can fine-tune it. So like, you can do stuff like this. I mean, you can go try it out. It's super fun, and then you can just play around with it, which is exactly the purpose of, what the purpose of making this follow me feature better was, to make sure that like, I mean, children can go and try it out, and then like, they can be like, oh, whoa, drone can follow me and I can control it. It's super sick. You know, that's what PX4 should do, in my opinion, for kids, not for developers, if you don't mind. And now we also have 3 altitude control modes. Follow height is in green arrow, and then so the simple mode, which was actually the previous upstream mode, is like 2D. It's pretty dumb, just follows you 2D. But there's a 2D plus terrain, which is pretty sketchy if you don't have an accurate distance sensor. It literally falls out of the sky sometimes, but you can try it out if you want. And then there's a 3D tracking, which is also broken because of QGC's bug, but you can try it out if you want. But there's a map SDK plugin, so with that, you're safe. But QGC, please don't try 3D mode. And yeah, I'll showcase the improved version. So these are two different cases where here I'm just running around, and here I'm riding a bike. And you can actually tell that there's quite a big difference in how it's tracking. Because in bike scenario, the velocity vector is pretty, its magnitude is pretty big, so it has a good target course estimate. So it seems smoother than me running around. But still, this is the end result, and in case you want to try it out, just feel free to do so. OK. But of course, there are many more things to be done. And I wanted to really showcase this to show that PX4 development is not just working on C++ side of code. First of all, there was a review process. This review process, I think there was like 190 comments, and it was like so many ideas, like, oh, why don't you name this like this? Oh, why don't you make a function do this instead of this? And like, so many people give you ideas, and then you first think like, oh, I mean, that doesn't sound really good. But then you realize like, ah, that's true, you know, that was so dumb to do this because now I have so many bugs. And you know, people give you so many good ideas, and this took like 3 months, but it was so worth it. And I'm going to link everything to my talk, and I have a GitHub repository where you can track all the materials. You can check what the review process was like. And yeah, I think you might get an interesting idea out of the review process from the Follow Me PR. And there was a comment cleanup because you know, there used to be 160 comments or something, and then squashed it, and now it's 3 comments, and master is cleaner. And yeah, I mean, I hope it helps the developers. And there was actually a really weird issue where it's totally out of the scope of the project, but we just couldn't get it merged because the board's flash was getting overflowed. I mean, I'm pretty sure you guys know about this. But basically, in the end, I was trying a lot of things, but Daniel jumped in and then removed some things, and I was like, oh, it worked, it compiles, okay, it's fine. So we got it merged actually last week. But there's mav SDK changes as well, because as I said, I changed how it transitions, how it follows you. So it had to change the mav SDK side, which was a lot of learning curve, because in mav SDK, you have a whole new file system. But that needed to be done. And PX4 user documentation as well, because you want the users to actually use this, so you have to create a PR for changing the user documentation. And of course, there's a whole new review process from Hamish, who's a really good technical writer. And then you can go into a lot of iterations and make sure that users will use it if the doc is good enough. And also, you need to add a functional CIDL test to make sure that your added feature works. And that was also a lot of work, because CIDL test depends on mav SDK, but because I changed the mav SDK's properties, you had to build a mav SDK locally and then build a CIDL test and make sure that it doesn't reference the upstream's mav SDK, and all of that was pretty complicated. But in the end, it was done, and now, I mean, the CIDL test works, so that's good. Yeah, so I'm a really not so experienced software developer. I'm still in bachelor's. But I think I learned a lot of stuff that's really valuable. And first is like, it takes a long time to develop something and like get it merged. Like, you have all this like weird issue, like board flash like overflowing. Who would have thought? Or like mav SDK changes. Who would have thought? And then like mav SDK side cannot get merged because the upstream PR for the follow me isn't merged. So you're like, oh, and then the master branch starts to pile up more comments, and you have to rebase, and then, you know, all this process takes time, which I didn't know as a, you know, not inexperienced developer. Oh, and this is something like that happened. Like, yeah, I was testing this, and I mean, I didn't even know, but like, I came back, I smelled something weird, and it was like a dog who peed on the jacket. But it's fun to test it out in the field. There's a few things left to do. Dog leash mode. Oh, it's ironic that it's dog leash mode. I hope, you know, dog leash mode basically would resemble what Skydio or DJI does. DJI and Skydio have a mode where you can actually run around, and it wouldn't try to aggressively go in front of you if you set it to follow in front. it would actually like come as if you have a leash and then drone is just hovering. And that's something I didn't implement yet because it's just going to add too much to the PR, but I think this would be a very good addition for kids and developers to play with. And the GPS offset compensation. Ooh, this was a tough one. So this was a controlled test where, so during the test, I noticed that like drone is going somewhere weird. And I was like, what is happening? And I did a control test where I put the drone, I made it take off, I went to the takeoff spot and then activated follow me mode. And turns out there's like five meters offset from the GPS, so it thinks like I'm like way there instead of being here. And this is unfortunately not possible to fix because the GPS sensor has its inherent offsets, and that's for a good reason for military, I think, so that like you don't have a super precise GPS. But this can be fixed with a vision-guided system or some kind of IR, like sensors, or if you want to try, like that we fixed, but currently it has this limitation. So this is a pull request in case you're interested. And that's it. So thank you so much for listening, and yeah, thank you so much for coming. That's all I can say. Thank you.
Any questions? I'm going to, oh, yeah.
You said that the trajectory generation had bang, bang on jerk, and then you integrate to get all the other orders. Is that in any way connected to like the second order reference filter that TJ made, or is this like two separate things?
It is separate because the second order filter only deals with filtering the GPS, whereas the jerk limited trajectory calculates the trajectory based on the follow angle and all the inherent properties. So second order filter deals with the GPS like external side, and the orbit trajectory is like internal side, like algorithm-wise.
And is that trajectory, I guess, third order then?
The jerk limited trajectory? Actually, how do you define something ordered? Because I didn't take class on that, I think. Like, how, I don't know.
If it's jerk limited, then it should be third order, I guess. Basically, how much level of derivative you can do on the trajectory until you hit a spike.
Okay.
Yeah. Kind of a discontinuity.
Yeah, so second order, you have your sending position, and you're, but you're producing velocities and acceleration commands as well. So that's why this is, I guess, third, because you're going one level above that for jerk.
Okay. Yes. I think I'll need to read some Wikipedia articles, but thank you for the question.
What additional functionalities are needed to implement the dog leash mode? Because it seems like you have almost everything you need already. Like, what's preventing that from happening? Is it just time?
Okay, so I was eager to add this, but you know, if you add another comment, there's another review process. Therefore, it was not added. But yeah, I think it's pretty much straightforward to add. And
would it just be like relaxing the exact position to just be a distance from the person or the target, correct?
yes, and it wouldn't even calculate the targets like horse, because dog leash shouldn't calculate that. Exactly, it's just gonna. Yeah, I'm not sure exactly how it worked, but yeah, maybe. Yeah, actually, I'm not sure. Maybe I have to think about it more. Yeah.
So for the GPS second order filter that you did, you said you do number of iterative filter, make it work on the data set, and then come up with a good result. Does that all happen on FMU? Because from my perspective, that would be a good amount of extra computation that you would have to do just to, you know, filter out the GPS data.
You mean the natural frequency selection part?
Yeah, yeah, exactly.
So as I showed in the early parts, that was first done in algorithmical stage, which is, where is it? Here, right? But in reality, it's actually different, and I actually couldn't figure out exactly why that happens. But in reality, if you try like in 2 radians per second, actually works pretty well in simulation. But if you actually try it, like it goes crazy, and I couldn't actually figure out why. But there was, so after verifying that, like, okay, the crazy limit in simulation is like 8, I started to tackle like 4 to 1 in real life, so that I didn't have to spend the whole time like flashing again 4 to 1 different parameters and stuff.
Okay, I got a question from Zoom. Any plans to add obstacle avoidance?
Ooh, that would be Skydio. I mean, if I had a sensor, I would have, I think, implemented it. But because obstacle avoidance can actually be stacked on top of the, like, flight control, and it's like it's gonna do obstacle avoidance on its own. So if you have obstacle avoidance sensor, it would work in follow me mode because it wouldn't crash. So it's a different, like, stacked, like, flight structure. But I didn't have the obstacle avoidance sensor. I mean, it had a distance sensor, but it was trying to crash the ground, so I didn't think it was so helpful. But yeah.
If you have a distance sensor that's looking down, could you use that to try and compensate for the geoid issues with GPS, or is it an issue because you have 2 GPSs, right, and you need them to be on the same coordinate system? Yeah, it's just interesting, because if they're both tracking on the geoid coordinate system, then it seems like it should work, but there's obviously issues. I was wondering if you could elaborate on how that's causing issues slightly more.
That's a very good point. So first, I thought because PX4 uses altitude above mean sea level as its like main reference point, it isn't, it's different from the phone QGC's one. But actually, it could be possible, I guess, to. Yeah. So the only reason was because in PX4 they have a vehicle home position message, your message, right, where it actually stores like a reference point where the home position is. And the follow me mode actually has an internal calculation where actually it projects the GPS received from the phone in reference to the home position. And the problem was that the home position's altitude is an altitude above mean sea level. But if you knew that it would come in geoid reference point, I think it would be pretty straightforward to just change that part where you actually reproject like a northeast down coordinate frame. Then it could actually solve that problem. But the problem was that Mavlink defines that it has to be in the altitude above mean sea level, and the QT wasn't, so it didn't really make sense to say, oh, we want to use geoid instead, because it would be out of the spec of the message.
One more question. Anybody? Okay. Thank you, Junwoo.
Thank you so much.